Number Theory, Section 3, Congruences and Modular Arithmetic. Video 3, Fermat's Little Theorem. You may have heard of Fermat's last theorem. It was quite famously proved in the early 1990s after many, many years where mathematicians couldn't get any sense of how to prove it. It's very worth looking up the story of that if you don't already know it. This video concerns another theorem by Fermat called Fermat's Little Theorem. Fermat's Little Theorem concerns prime numbers and states that if p is a prime number, then for any positive integer a to the power p is congruent to a mod p. And if p is not a factor of a, this statement's equivalent to saying that a to the power of p minus 1 is congruent to 1 mod p. Let's have a look at how that works in practice. So here's a couple of examples. First of all, when n equals 5, 1 to the power 4, 2 to the power 4, 3 to the power 4 and 4 to the power 4, you can see that 1, 16, 81 and 256 are all 1 more than a multiple of 5, so they are all congruent to 1 mod 5. And since 5 is a prime number, that's what Fermat's Little Theorem would tell you to expect. If p is a prime number, then a to the power of p minus 1 is congruent to 1 mod p. Let's have a look as well then at n equals 6. So 1 to the 5 is 1, 2 to the 5 is 32, which is 2 mod 6, 3 to the 5 is 3 mod 6, 4 to the 5 is 4 mod 6, and 5 to the 5 is 5 mod 6. So since n is not prime, we're not getting this result where all of these are congruent to 1 mod 6. Now you don't need to know how to prove Fermat's Little Theorem for this course, but it is worth looking at an outline of how to prove it, and you might want to read up some proofs online to give you a little bit of sense of how it works. So in order to see how it works, an outline of how the proof works, I'd like to show you what happens when p equals 7. And I'd like to imagine all of the different values that a could take and consider what happens with a, 2a, 3a, 4a, 5a and 6a. So if a is 1, then I simply get 1, 2, 3, 4, 5 and 6. If a is 2 and I'm working mod 7, then I get 2, 4, 6, but 4 times 2 is 8, which is congruent to 1. 5 times 2 is 10, which is congruent to 3, and 6 times 2 is 12, which is congruent to 5 mod 7. So I'm just filling in the values mod 7. So 3, 6, 9 is the same as 2, 12 becomes 5, 15 becomes 1 because it's 1 more than 14, and 8 becomes 4. And as I fill this in, I hope you can see that on each line I'm just getting the digits 1, 2, 3, 4, 5 and 6 permuted somehow. So this means that whatever value I choose for a, 2a, 3a, 4a, 5a and 6a gives me the set of numbers 1, 2, 3, 4, 5 and 6 in some order mod p, mod 7 in this case. Now what I'm going to do is I'm going to multiply together both sides here. So on the left hand side I've got a, 2a, 3a, 4a, 5a and 6a. So I've got a to the power of 6 multiplied by 6 factorial. I'm going to write that as 7 minus 1 factorial because we're considering the case p equals 7. And then on the right hand side I've just got 1, 2, 3, 4 and 5, 6. I've just got 7 minus 1 factorial. So a to the 6 times 7 minus 1 factorial is congruent to 7 minus 1 factorial mod 7, which means that a to the 6 is congruent to 1 mod 7, dividing through by 7 minus 1 factorial. Let's see that a little bit more neatly. So considering the case p equals 7, a, 2a, 3a, 4a, 5a and 6a is the same as 1, 2, 3, 4, 5 and 6 in some order mod 7. Multiplying together all of these gives me a to the 6 times 6 factorial. Multiplying together all of these just gives me 6 factorial. So a to the 7 minus 1 times 7 minus 1 factorial is congruent to 7 minus 1 factorial mod 7. So a to the 7 minus 1 is congruent to 1 mod 7. And for p prime, you're always going to get this permutation happening of the different congruences. And if p is composite, that's not going to happen. So that means that whatever you do, you're going to get that a to the p minus 1 is congruent to 1 mod p in the case where p is a prime number and p is not a factor of a. In this video, you've learnt Fermat's little theorem and you've seen an outline of how to prove Fermat's little theorem.